So welcome to the 10th class of Big Data Analytics. Today we will be covering analytics on graph data. So analytics on graph data is the last major big chunk or big block of knowledge that I would try to equip you with for this class. Okay. Now let's make sure we're on the same page. Once again, this class is about performing analytics on data, right? And for the purpose of organization, I kind of separate the content or tools and techniques into three lumps or three classes, right? One is interactive visualization. That means that if you know how to plot the right axis, you allow the user or the client to be able to interact with the graph, try different axes, try different ratio, different juxtaposition between different series of data. That is going to give you almost immediate insights, actionable insights. Okay, so the keyword is actionable insight. So that will be lumped under what I call interactive visualization. Okay, so in this textbook, right, interactive visualization is basically chapter 3. Okay, it's this chapter, right? Now this chapter has two parts. The first part deal with all the visualization schema that you can use as exemplified by built-in function in Mathematica, and the second part is where we endow all the display with parameterization and make those parameterization into adjustable knobs, so to speak, using manipulate, right? So the first part of so the chapter 3, the first part is static visualization. What kind of visualization tools can we employ? Second part is interactive, just make them interactive. So that is basically chapter 3. So that's the first big group of what I call the types of analytics you perform on data. Okay. Now, chapter 4 then proceeds onto statistical, probabilistic, basically probability and statistics. This is more the classical way of dealing with data. Again, it's more amenable to traditional data, not so much big data where you have a lot of variety like colors or video file or image and all that kind of stuff. So it really is mostly applicable to numerical data, right? In particular, you tend to have some kind of assumption as well in terms of the distribution. You have to sort of like think of it as, well, maybe this thing has an underlying distribution. It follows Poisson distribution, follow normal distribution, and so forth. And then if all those criteria are met, you're working with mostly numerical data that has certain numerical probabilistic behavior that is typical of certain class of probability distribution, then you should use this because it's very powerful. You can perform statistical tests, you can do rejection, hypothesis testing, p-value and all kind of stuff. So it's very powerful, but it's limited. Okay. And then the last group of data analytics, which I call machine learning based. Okay. Right. Machine learning is not limited to data analytics. Like I said, machine learning applies to so many things. So a good example would be robotics require machine learning, right? But robotic is not data analytics. It's doing a job. It's not analyzing data or helping you do so. So for data analytics, I'm going to limit to that part of machine learning that is good for delivering insights about data, okay? Which means that of the major machine learning paradigm, and I may ask you what the major machine learning paradigms is, in, say in an exam, right? So unsupervised learning, supervised learning, reinforcement learning, and maybe in the future, some kind of embedding or representational learning. Okay, but or maybe in graph learning, but the most important aspect, the two key machine learning paradigm that's applicable to this class are what? Supervised and unsupervised, right? Now that then is treated in chapter 5 and 6. 5 would cover. 5 is where I go over the unsupervised learning, and 6 is when I go over supervised learning, all right? And again, I did mention that even though these are treated in 2 separate chapters, and a lot of application would be, strictly speaking, an unsupervised learning exercise. Some job require you to do supervised learning. Occasionally, you use them together. Okay. Sometime, for example, a good practice that I find in my own practice is that unsupervised learning does a lot of cleaning or reducing extra dimension so that when you perform learning, you actually get to the essence of the pattern of the data. Okay, so you might even get unsupervised learning first and then feed that into supervised learning. Or you can do supervised learning, but the result can be visualized using some kind of dimensionality reduction, which is part of unsupervised learning. So they complement one another. Okay. Now, here's the deal. Chapter 7, which is the subject of today, okay, is dedicated to performing analytics on graph data. There's a reason why I treat this separate. I could have kind of like snuck bits and pieces of graph data in the earlier chapter, and I think I did a little bit of that as well. But there's a reason why, at least in my book or in my thinking, I treat that as separate. And within graph data, okay, first of all, with graph data, what kind of analytics can you do? Well, actually, all the above analytics, interactive visualization, okay, yes, you can do that. In fact, that's very important. Probabilistic or statistical modeling, some of it you can, but it's very difficult. It's very limited. Okay, so I'm not saying that if you have graph data, you can't use a statistical model. There are statistical probabilistic model that mathematicians have come up with over the years that's very applicable to graph data. Okay, but in my experience, at least, it's not that there aren't that many of those. There aren't that many of you can do with. Not too many things you can do with. You can do statistical property like large network or random network, that sort of thing. But when you want to study particular network, like network of friends, network of supply chain or something like that, then statistical properties are not that great at helping you. Okay, so that leaves what? That leaves machine learning, right? So you're going to have machine learning apply on graph data. Now, machine learning apply on graph data. Once again, we have the 2 major paradigms. One is unsupervised learning, and the other one is supervised learning. Okay. Now, supervised learning on graph data, in a way, is part of data analytics, but it's better explored in another class, like in the machine learning. One of the reasons is there's been a lot of growth in the past 2 or 3 years. Actually, yeah, 3 years, let's say, no more than that, but 3 years, where learning on graph data just really took off. Okay, I'm not talking about social network analysis here. Okay, social network analysis is old news now. Okay, I'm talking about actually learning to do some kind of prediction, so they're like a deep learning on graph structure. Okay, that's really taken off in the last 2 or 3 years. So it's not part of what we're going to cover. Now, what we are going to cover is unsupervised, one kind of what you can think of as unsupervised learning, or basically algorithmic some sort of computational algorithm that allows you to analyze data. And that's what we're going to talk about today. And that's called a centrality analysis. Okay. If we can get to, I'm going to also show you that there are some computational approach to analyzing graph data that does not rely on machine learning. Just pure graph computation, basically linear algebra. Okay, there's some of that as well. If we get to that, that'd be great. If not, maybe next week or so. Okay, So you can see that, 1, 2, 3, 4, 5, 6 is kind of like one book. Okay. And chapter 7 is like the same book, but just on the graph. Does that make sense to you guys? Okay. Does that make sense to you guys? Now, why do I do this? Why do I do this? Well, let me draw a little picture here. Let me switch. Okay. Stop share or something. Stop share here. And I'll go to big screen. Okay. Okay, good. Let's be this one, I think. Yeah. It's not plugged. Okay, maybe go back to this. I'll do hand waving. Okay, go back to this guy. Okay. Look at this piece of paper. Okay, maybe I can use draw or something. Actually, I have a description of it a little bit here. Let me go to that part. You should have it as well. So in chapter 1, if you go down to a generalization here, there should be a part. Okay, there you go. Right. Okay. Think of, remember I told you that even though we have this big data, bulk of the data that you're going to be dealing with is going to come in a table, right? What does a table look like? It looks like a spreadsheet. Okay, so each row corresponds to one data entry point, right? So if you have 1,000 row, that means you have 1,000 sample or 1,000 data point. And if you have 50 columns, then that means that apart from maybe the first column or first couple of columns that's used to identify as an ID field, right? These are informational attributes, okay? So maybe the first column is student ID, right? So that's basically to identify who you are. But column 2 to column 50 is information about you, okay? Your height, your weight, your sex, your where you live, how many years have you been in college, whatever, okay? Just information about you. So each one is a line, right? The point is this. The dimensionality of the data is basically, quote unquote, the number of columns. Okay, so as many columns as you have, that's sort of like the dimension of your data. Okay. Obviously, if the dimension is a physical coordinate, then you have 3 numbers, right? X-axis, longitudinal, latitudinal, and maybe sea level height or something. I don't know. Okay, right, and all kind of stuff. So that's clear, right? That's clear. What's important is this. I can write X subscore I. Now, think of this in your head. Take X underscore I. X represents the vector of information. So that's all the columns. What's I? I is the identifier, which could literally be your student ID or maybe just the row it's in. Okay. So for example, X7 would be, take this table and go down to the 7th row and read that. Maybe the first one is student ID, second one is first name, third one is last name, fourth one is birthday, age, sex, years of college education, God knows what, right? So this is very important, right? You have information indexed by the identity to which the information belongs to. Okay, I just start using words like attributes. So it's attribute of that entity. Okay, so you are an entity, you have attributes. We measure those attributes, years in education, height, age, sex, whatever, blood pressure. Okay, those are attributes that pertain to you. Okay, this vector X sub I has only one index. Has only one index because the information contained in that X, right, pertains to the I data point. Okay, so that indexing, okay, refers to the entity to which X belongs to. Okay, now let me ask you a question. In which circumstance would you have more than one index? Well, a screen display, for example, has two index, right? There's a horizontal and there's a vertical, correct? So you can say that go down this row, horizontally, this many pixel, and go down this many pixel vertically, and you get to that color, right? And we talk about, a tensor being another dimension is the three color, red, blue, and green. Fine. So it looks like it has two index, right? So color sub ij. Okay, let's say C subscript ij, I being the pixel down, j being the pixel across. Okay, now I'm going to tell you or ask you to think, is that really necessary? Actually, no, you don't need two index. The reason you have two index is because it's convenient, right? It gives you a nice way to reference, right? But if you have 1,000 pixel on the first row, right? The first pixel on the second row need not be 2,1. It could be 1,001, right? Does that make sense? Right? So yeah, you have two indices. Right? But the entity that you point to, there's only one entity, and that's the pixel. Okay, so even though you have a pixel 3,2, okay, you could use one index. Instead of 3,2, you would say 3,002, right? 2002, because you go 1,000, 2,000, and 1,2. Okay, so this is what I kind of want to use a handwritten thing for. Okay, so a screen index, right? The screen index has two index, has the vertical index and horizontal index, but theoretically that's just convenient. Theoretically, it's just one index because the information belongs to only one entity, only one pixel. Okay, so you have to ask yourself, is there a situation where you have data that never ever belongs to one entity, so that no matter how you represent the data, you always require two indices because that information belongs to two entities. Okay, so this is a way of thinking about data from data up. Okay, if I were teaching you to teach you guys from a graph theoretic perspective, I'll start somewhere else, but I'm starting you guys from a data perspective. From a data perspective, think of any kind of when would there be kind of information or attribute that does not belong to one person or one entity? Okay, now I mentioned that things like years in education, right? That's you, right? You went through the education. Okay, so for this for you right there, the number of your education is 11.5 years since whatever. Okay, since grade school. Okay, now think of situation where I cannot index number of years with one entity. Well, think of marriage, right? You can say, okay, this guy got married. Fine. How long has he been married? So maybe he's been married for 20 years to 5 different people. Okay, that's him. That's his information. So that only requires one index. However, there is one information which is a particular marriage. That information always requires two index. Okay, so Bob married to Alice for 5 years. That's it. That 5 can never be referenced to Bob, because Bob could marry Alice, get divorced, and marry Chris, and marry Jane, and whatever, right? Okay, so that's his number. But the years of marriage between Bob, who is the first wife, Alice, right? So let's see. Okay, Bob married to Alice for 5.5 years, say. Okay, that information can never be indexed Bob. It's always indexed with Bob and Alice. Okay, now notice this situation is not either or. When you have information that belongs to two entities, it doesn't mean that the first guy loses his identity, right? Bob still has his height, his weight, his years of education. So this kind of data is a generalization of your data. Okay, so it's tabular data. That's I, correct? Technically, I is the row. Okay, in this case, wait a minute, you can never have just I. You will always have IJ pair. Okay, start using this word. Okay, it's good that I use a marriage as an example, because when people get married, they're called a pair or a couple. Okay, but both words are actually valid in mathematics, but in mathematics usually use word pair. You don't say couple. Okay, couple usually sometimes it's used for something else. Like okay, so right. So now, for a population of n entities, think of n entities, okay? How many row of data can you have if you're talking about tabular data? I don't care how many dimensions you have, you can only have n row. Yeah, you can only have n row. Okay, because that's index I equal to 1 to n. Now think of tabular data. Think of this pair data. Now I'm going to use the word graph data with a definition, but that's what it is. With graph data, if you have n entities, how many entries do you have? N square. Okay, and this is where I wish I could use the whiteboard. Okay, but you could just look at my hand instead, right? Now, the example that I mentioned, Alice and Bob. Okay, there's one piece of data called 5.5. That's the years of they've been married together. Okay, this data, okay, y sub Alice comma Bob is always equal to y index Bob comma Alice. So Alice comma Bob or Bob comma Alice is the same thing, right? Right? Okay. So you can think of this as symmetric, right? The relationship is not equal. Maybe somebody loves somebody more. I don't know. Okay. But at the end of the day, the number of years they've been married together is symmetric. Okay. Now, let me ask you another question. What if I'm not recording the number of years that Bob and Alice have been married? Let's say the number of years that one person knows the other person. Okay. Now, Bob and Alice could meet each other for the first time together, right? So that the time when they start to know each other is the same. But sometimes you can know one person without the other person knowing you, right? Right. So maybe Bob has been, looking at Alice's profile in the Facebook for 2 years before getting enough courage to ask her out or something like that. Okay. In which case, the number of years I knows J is not the same thing as number of years that J knows I. Right? So Y subscript Bob comma Alice is not the same thing as Y subscript Alice comma Bob. Right? So think of this matrix in your head, right? But all the population people in the world, okay? So now you need both vertical or horizontal and vertical just to line people up. Right? Just to line people up. Okay. So now we have you can say three kind of data, right? There's a data that that belongs to Bob comma Alice. There's data that belongs to Alice, comma Bob, which even though it's the same number, same field, same type of information, it's not the same number, right? And then there's of course data subscript Alice, and data subscript Bob. So that's sort of like data that belongs to oneself. Okay, you can think of those as diagonal data. Okay, diagonal data. Okay, does that make sense? Now, think of the variance covariance matrix. That's exactly the first instant where you saw this. If I have 400 Thai share, roughly, that's a rough number. Let's say in the Thai stock market, there are 400 publicly traded companies, large company. There's 3,000 more in MAI, but in SET, there are 400 companies, right? Right? Now, in this case, you have the volatility of stock price of company 1 to company 400, right? Then you have what's called correlation. Now, it turns out that in this case, it's completely symmetric. Correlation between PTT, EP, and correlation and another company, say, I don't know, SCB, would be the same thing as correlation between SCB and PTT, EP, right? In which case, IJ and GI is identical, okay? But that means symmetric, okay? Symmetric. So that's it. Now, so that's from a data perspective. You okay with me, right? There's no way you can reduce this kind of information to one index. Okay? You can't. It always belongs to two entities. Okay? So index is not just a matter of convenience now. It's just about reference to entity. Okay? How many entity does this piece of information belong to? 5.5 is not a number that belongs to Bob. It's not a number that belongs to Alice, but it's a number that belongs to Bob and Alice. Okay, good. So why do I call this a graph data? Are you sure I can't draw a picture? I need to draw a picture. Otherwise, I have to go to the internet or something. Oh, actually, I don't have to go to the internet. I can go to my own graph. Okay, so look at this. Let's try one more time. If it doesn't work, it's actually, I have drawn plenty of graph in the note in the textbook, so you can actually see example there. Okay, so let's see what happened. We go to flip this. Okay. Ah, good. Now, it's actually in here. It just takes me a while for me to get to it, so it's easy for me to draw. Okay, now. Okay, this is X coordinate, this is Y coordinate, right? Now I'm just going to try to confuse you. Okay, I'm trying to confuse you. Okay, this is data point number 1, this is data point number 2. Okay, data point number 1, number 2. Okay, and this is location. So actually X1, Y1 is actually what? 2 pieces of information that tells location, right? But that belongs to 1. 2 has another number, right? And if it's 3 dimension, you can do it. So this is what we call tabular data, right? Two entities. Okay. Now let's make it Z. So there's another dimension. Z1, Z2. 2 entities. Each entity has 3 dimensions. Oh, okay. So these are the attributes. And this is the entity ID or something. Okay. Reference ID. Okay. That's what we were doing. That's what we've been playing with. Okay. That's what we're playing with. Just to keep emphasizing past knowledge. If I have this kind of thing and I want to know who cluster with whom, that's unsupervised learning, right? If I have something like Q1 and Q2, where Q is a label, say boy or girl, and I want to use this to predict, that would be what kind of problem? Supervised learning. Okay, good. Just review. Okay, let's review. Okay. Now, here's an interesting. So, and again, this is the pixel example. So if I have 1,000 here, 1,000 here, and then 5 here, right? I can call this one 5. Oh, sorry, 3, 5. But it's the same thing as 2005, right? It's just one index. Just go 1,000, 1,001 to 2,000, 2001 to 2, 3, 4, 5, 2005. Same thing as going down 1, 2, 3, 1, 2, 3, 4, 5. Okay, so that's that. But again, this one has 2 index, but the information only belongs to how many pixels? 1 pixel. All right. So that's not what I'm talking about. Now, let's just say Alice and Bob. Now, because we can't do monogamous anymore, we have to do many. So let's say number of years they've been friends, friend network. Okay. Okay. And this is Jane. Okay. Okay. So Alice and Bob have been friends for 10 years. Bob and Jane have been friends for 7 years. Something like that. Does that make sense? Does that make sense? So now, how am I gonna put this kind of data information on a table? Well, I can't have table that just say, Alice, Bob, and Jane. I have to do another one here. Alice, Bob, and Jane, right? Right? Now, this one is irrelevant because, maybe you could put the age. Everybody knows himself or herself since they were born, I guess. Okay. Now, so that's what I'm talking about. Now, I start drawing this schematically. Okay. So obviously, if I have 1,000 friends and I have a whole bunch of number, it doesn't look very easy. It's not easy to visualize. So think of this as a visualization. Okay. Now stop. Start again. Start over. Now, mathematician comes in. He comes from different perspective. His perspective is to start with the representation itself. 1, 2, or A, B, C, D. And these are the, say, connection. Okay. I'm going to draw all the connections. All the connections. Okay. If there's no connection, the value is equal to 0. Right? So you can say that if this person doesn't know this person, this line has a thickness of 0. Okay. If this one knows this one for 10 years, has a thickness of 10 millimeters. Does that make sense? Yeah. That's a very nice way of looking at it, right? Okay. Mathematicians have been working with this in a very abstract form for over 300 years. 3 or 4. Okay. Anyway. The famous case of this is it's a little. Well, I'll just give you a funny story. There's a little enclave of Russia that's actually on the Baltic Sea called Kaliningrad or whatever. Okay. Well, in the old days, it used to be called Königsberg. König means king, so it's like a king's town, king city, or something like that. Anyway, so what they had was they have this geography problem, and they have a bridge. They have a whole bunch of, I think, a bridge, and a bridge, and bridge or something. I don't know. Okay, whole bunch of bridge. Okay, and it's called 7 Bridge of Königsberg. 7 bridges. 7 bridges. Now here's the deal. There's a mathematical puzzle. They ask, can you cross all the bridge only once? Okay, so you can do this. In this case, you can, right? In this problem, you can. But the 7 bridge, I think it turns out you can't. Now, how can you prove it? How can you prove it? Okay, how can you prove it? Well, the answer comes from the fact that what they did. Now, I don't remember the layout of Königsberg's bridge, but instead of thinking of bridge and land, think of land, 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 bridge, 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 bridge. Right? Right? So it turns out, okay, that there's some property about bridge, like if you're going to cross things once, each land must have the number, even number or odd number of bridge or something like that. Now this one, you can do that. You can do it like this, right? But if you have something like I don't know. I look up the Königsberg. I don't remember. It's got 7 bridges and however many landmass. The point is, it was conceptualized, has nothing to do with data. Okay, it's not about how many years has the bridge been built. Okay, but once that thing became mathematical formalism, then this is what we call graph. Graph is a collection of vertices and edge. Okay, vertices are the lines, edges are the entities. Sorry, vertices are the entities. Okay, so let me write this out. Vertex. Now, for those of you who came from social network, you may not be familiar with this word, but you might be familiar with another word, nodes. Okay, nodes. And this one you may use the word arcs. Okay, but mathematicians tend to use vertices and edge, so I'm going to stick with that, V and E. Okay, so a good example. Now let me ask you, who are the entities? That's the vertices, right? If there are n vertices, how many data point do you have? It's n squared, right? So let's go from V1, Vn, V1, Vn. Right? Now, when I draw something like this, a bridge from A to B is the same thing as a bridge from B to A, right? Right? Now, what if we make it a road bridge and we allow for one-way travel? Now maybe in 2 cities, right? You can have one that has an arrow like this, right? This is not the same thing as this. In which case, something like this, you can come, it's a one-way, you can't come back, okay? So this case, if this is I, this is J, right? And this is Bij, and this is Bji. It's equal to 1 if it exists, okay? Forget about number of years, just say yes or no, okay? Do I know you? Do you know me? That sort of thing, okay? Now, knowing is not the same thing as friends, right? If you're a friend, that means you know each other, correct? So it's kind of supposed to be symmetric, right? However, you can be friend with I don't know, Taylor Swift in the net, in the Facebook, but you're not a friend in the sense that you are a friend. It's sort of like you follow, right? So it's not symmetric, right? Right? So something like if this is no, you can imagine that celebrities over here, and there's 1,000, 1,000,000 follower, right? But maybe this celebrity only knows 5 people, or is a friend with 5 people, right? So definitely it's not symmetric. Okay. So back to definition. So the edge, E, I, J, okay, is a number. Yeah. Now I'm using the word number. What happened? You guys should already think about nominal, ordinal, interval, ratio. What kind of number scale can this belong to? Okay, what kind of number can this belong to? Now, in this kind of application, if I say EIJ is the number of years that one person and the other person knows each other, what kind of number would that be? Ratio, right? Because it could be continuous number, but it starts at 0. So you know where S0 is. It happens to not allow negative number. But let's say if you can measure how much one feel about each other, okay? Maybe a maximum of, I don't know, 100 or something. So if you love somebody, absolutely, it's plus infinity. If you hate somebody, negative infinity, but you still have 0, right? 0 means you couldn't care less. Okay, you don't love, you don't hate, that sort of thing. So this is a ratio number. It's a ratio number, right? Ratio number. But what about if I only say, okay, there are 3 categories of relationship. Okay, you a friend, you a classmate, and you are in the same club. Okay, yeah, friend, classmate, club. Okay, how many types of relationship can you have? It's a trick question. How many relationship can you have? How many types of relationship? 8. Right? Why do I say 8? Because you can be nothing, not connected. You can be friend and classmate. You can be friend, not classmate. You can be friend and club member. You can be friend and classmate and belong to the same club, right? Right? But anyway, this number is discrete, right? Discrete. So let me try again. So let's make life easy. Let's make it exclusive. Okay. Sorry. You have to be one or the other. Okay. So and a good example would be class project. Right? Class project. You can be class project with this person, and this person is a class project with you. But if you're not from the same group, you can't be. So class project is a either or. Okay, either or. Okay, so it's 1 or 0. A lot of the relationship that you use would be like this. Okay. Now I don't know. I'm not quite sure what Facebook is. Facebook only has what, friend and no friend, or I think anybody. I know Facebook is for old people, but you know, like. Okay, I'm just going to make this up. I'm going to guess. Okay, Facebook may probably, let's say, has friend and follow. Let's make it that way. Okay, so with friend it's symmetric. With follow it doesn't have to be symmetric, for example. Okay, now what if another application comes along, and instead of let's forget follow, let's just have friend. What if they have friend and best friend? Okay, and automatically if you're best friend, you're not considered just friend, so you get different kind of a messaging algorithm or something, right? So in that case you have 3 category: nothing, 0, 1, friend, 2, best friend, something like that. What kind of number would that be? I would say that number is kind of ordinal, right? Because 0 is certainly less than 1. 1 is less than 2, but you can't say, you know, how much is it better to be a best friend as opposed to just friend? You can't measure that. So, you know, friend, no friend, best friend. That's an ordinal scale number. Okay. Now, let me spare you the detail. Just as in a tabular data, you can have 500 dimension. right? You can also have 500 dimension of relationship. Yeah. So consider Bob and Alice. They have 5.5 number of years they've been married. They also have 10.2 number of years they've known each other. They also have 7.5. That's the age difference. They also have something like I don't know, 120 kilograms. That's their weight together when they want to travel together or something in a balloon or something. Okay, so obviously when you have two index, this graph, you can have many graphs. This is called multiplex or multi-channel graph. I will spare you this, but in life, yes, that's a situation. But in this class, okay, in this class, there's only one channel of relationship. Okay, so if I'm talking about a friendship channel, it's a friendship channel. If I'm talking about a marriage channel, it's a marriage channel. If I'm talking about project channel, it's a project channel. Okay, so don't worry about, in other words, Xij is one dimensional, just one number. Okay, it belongs to two entities, but there's only one number. So in this class, okay, I'll just give you the word for it. When you have more than different connectivity types, is called multiplex graph. Okay, plex is like channel. Okay, multi-channel or multiplex. Okay. Sometimes they call it multi-dimensional, but you can get confused. So I don't like to do that. Yeah, multi-dimensional, channel, or multiplex. I use the word multiplex because in graph learning, that's the technical word. So I'm just going to tell you this, okay? But in your class, it's always just one number. In other words, it's a scalar. Okay, so that's it. That's all you need to know. Two entities, n of them, right? Each pair or by itself along the diagonal, there's a number. That number could be nominal, ordinal, all right? Interval or ratio. Okay. Okay. Now, let's get to computation. Okay. So we have to go back to stop share. Okay, I'll let you do that. Okay, so that's the definition. Again, I use the word vertex because that's the most common scientific name. You can use the word nodes as well. You can use edge and arc in mathematics, and in most of the formal treatment, you use that. Okay, fine. So a graph in this case is not the graph like that's called a plot. Okay, so it's very important that once you get educated, when you hear graph, you don't think of plot. Okay, those quote unquote graph function, that's called the plotting function. Okay, so a graph is very specific. It's a collection of vertices connected by edges. Okay, good. So tabular data is treated from chapter 1 to whatever, chapter 3, 4, 5, 6. And this is treated in final chapter 7. Okay, so let's go to chapter 7, right? Okay, chapter 5. Okay, so this is exactly what we talked about. Okay, now this is an example. Okay, I'm just going to walk through example, and because you have in previous class, I've been kind of a bit mean. I wanted you to kind of like key in so that you get the experience, but I thought maybe sometimes it's not the best use of time. So you have it in front of you. All you have to do is shift enter. Okay, but follow the narrative. So I don't know, and sometimes I'm a little bit too mean, and I think it's good for you, but sometimes it's not time efficient, I guess. Right. So what I did here is, see, this one is blue. It's a variable. It hasn't been assigned anything. Okay. Adjacency matrix example data. Now let me do this. So if I take this, you guys remember that example data, right? Hello. Okay, because it uses internet. Okay. Now, actually, this is a misleading thing. When you say example data, you should get the raw data. So what you should get would be the matrix. Okay. Now I'm gonna make it you don't have to read the description. These are the casts of Les Miserables. Okay, it's a play, it's a musical play. Okay. Now the line, this one, each one is a character. Okay, each one's a character. Each line represents the fact that these two characters appear together on stage. Okay, so let me ask you this question. What kind of number is this? It's clearly nominal. In fact, it's 0 and 1, right? Yes or no? Yes and no is the simplest kind of nominal data, right? You don't have to name it, just say yes or no, all right? Did A and B appear together on the same stage? Yes. And is it symmetric? Yes. It doesn't matter if it's a big character or small character. If it's on the same on the stage at the same time, there's a line in it. Okay. So you can think of, I don't know how many characters. Let's say 50. Long time ago, I haven't seen the musical when I was probably your age when I saw it. Let's say there are 50 characters. Okay. And there's a line connecting each of them. And if they never appear together on stage, the line has 0 thickness. That's why you don't see it. Okay. But if they appear together, there's a line thickness of 1 millimeter. So you see it. Okay. You see it. Now, right away, you will notice that each character has a name, right? But here it's not shown. So the data should be like a list of casts, a list of casts. So basically a square matrix, 50 by 50, 50 by 50 matrix of 0 and 1. Okay. Now, because Mathematica knows that you're working with data, it automatically plots the data for you instead of giving you 0 and 1. Okay. But if you import this data from CSV, like somebody goes to a play and record who's with whom, right? You would get tables of 0s and 1. Okay. Right away, if I show you this, what can you tell me? I can show you this in an exam. What can you tell me about that matrix? First of all, you can count number of 0 and say this matrix is 50 by 50. Right? 50 by 50. Second, you can say that because the line has no arrow, it's symmetric. Ij is equal to ji. You can say that the matrix is symmetric. Okay. Now, I'm going to give you another word. When the matrix is symmetric, the graph that you draw has no arrow. The word for it is called undirected graph. I should write, but okay, undirected. So if you take the data from a symmetric matrix and draw it into a graph, the graph will have no arrow. Okay, has no arrow. Okay, you can think of it as it has arrow going to and from, but you might as well not draw an arrow. Okay, so undirected. You can go from I to J or J to I, same thing. If I show you another picture, well, first of all, there's also not a line from the node to itself. So this is strictly speaking graph data. Okay, so the individual age, sex, or importance of each character is not represented here. So the diagonal entry is 0, nothing. Okay, so if ij doesn't appear together, 0, nothing. I also, the diagonal on the I, also nothing, because we don't care about individual part, okay? And moreover, ij, ji, if ij is equal to 1, ji is definitely equal to 1, so symmetric. If I show you one that has arrow, then you would know that it is asymmetric, okay? Now, here's the thing. A lot of time, for example, in an exam question or in terms of analysis, you can't do detailed computation, but I can certainly do this. I can show you a picture of a graph that has arrow and a graph that doesn't have an arrow. And I say, this is a graph representing the number of years people have been friends with on Facebook. Which one could it be? Okay. You would definitely have to rule out the one with the arrows, right? Okay. But if it's, you know, things like follow, okay, then it will be arrow. So you can do, you know, matching, what do you call that? The matching exam, whatever. Okay. Match A with B. Okay, fine. So that's what the data looks like. That's what the data looks like. Okay. There's actually name of character, but for brevity, I kind of ignore that. So this is what we did. So I download this. Now, even though this is a data, okay, I want to see, let me do this. Let me take the word dimension. Okay, well, yeah, let me show. Instead of the word dimension, I'm going to change it to matrix form. See? See that? Now, this example data, that matrix that describe who is connected to whom. There's a technical word for who is connected to whom. It's called adjacency. Okay, maybe not a great word, because adjacent means like next to. Okay, now in this case, not necessarily, because when you appear together on a stage, one can be on the right side of the stage, one can be on the left stage, right? It could be a big scene like a mob fight. Okay, these two people never talk to each other. One's way over here, one's over there, so they're not that close together, right? But in terms of adjacency matrix, yes, there's a connection. So adjacency, don't think of the word adjacent like next door. Okay, it doesn't mean that. Okay, it's just a technical term they stick with, and you know, we'll stick with that. Notice, right? So that's the matrix. You will notice that on the diagonal there's 0, because you know you're not connected with yourself, even though you are. Nobody care. Here, the first character and the second character have appeared together with the third, fourth, fifth, seventh. Okay. So you can think of ij as whether or not I appears with j. And of course, if you flip this thing along the diagonal, the transpose of this matrix is exactly the same. Now, so let's go back to dimension. The reason I didn't mention, okay, that's a character count, right? 77. So how many cast member in the play? 77, right? Right. So this one is called edge count. Okay, edge count is a number 254. That means that there are 254 ones. Well, actually, you can do it easier than that. You can just say, you can just take this thing, right? Oops. Right? By the way, it looks like this, right? And then you just add total. Okay, now this adds total along the row. Okay, so let's do it twice. 508. How come I don't get the same number? Because it double counts, right? The edge is, so divide by 2. So you divide this by 2, you get that, obviously. Okay. Yeah. So the reason that sometimes they list this edge count separately, because it's a bit tricky between connected and not connected. Okay, so this is the one. I say I take the first 20 to display it, but we already saw that actually, so we don't need that. Okay, Now, there's all kind of function. There's all kind of function. This would give you sort of like a built-in, this whole host of thing. I just select whatever I think is interesting. List density plot. Now, list density plot is basically heat map, okay, of that matrix. In this case, obviously, the connection. Now, this one happened to go from, instead of so you guys remember from the first guy, right? The first one knows all share screen with the other 8, right? See that the first guy share the screen with the next 8. Can you guys see this? Okay. See that the first guy, the first character, whoever that is, we don't care about names. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's this one. Okay. Whoops. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So character 1 and character 2 to character 9 appear together. Okay. And vice versa. Okay. So, right. Let's see what does. Normally just some kind of now, that's one example. In this case, I just make up some other thing. Now, this is what's called random graph. In other words, instead of draw the data from actual play, I just create this thing called random graph. Okay? But random graph has a way of creating sort of like a density. You know, if it's very dense, very sparse, very rare. Okay. So this is just a three case. Okay. Now, what happened is when you look up the word random graph, so F1, oops, I keep forgetting that this thing would crash every time I go to F1. Sorry. How do I do that? Okay, I have to come back. Okay, you go to F1, you go to help screen, right? This one does it. Okay. Basically, I just make an example. Yes. You guys okay? Follow that, right? So what I did was just waiting something. Okay. Some example. Now here's the concept I want to start talking about. Okay. You can do all kind of analytics, non-machine learning analytics, and in fact, I'll show you some of that later. Okay. For example, you can say, is the node network there? Is it completely connected? Completely connected means everybody knows everybody. Okay. So I'm just going to use friend network as an example. Okay. So completely connected graph means everything is connected. Yeah. Dense graph, dense is kind of like an additive. That means, roughly speaking, most everybody knows most everybody, right? It's not a precise term. Opposite of that is sparse. Sparse means thin. So basically, look at this matrix of 0 to 1, right? If it's all filled up with 1, that's completely connected. Okay? If all connected. If it's very densely connected, a lot of people in this is a close tight community, right? Tight community, then you have very dense graph. But if maybe the next person, so everybody in the way, you can send a line message. You can send a message from here to this guy, and eventually everybody's connected, but not immediate. Takes a number. So the word connected and the word immediately connected are not the same, right? Right. If everybody is sorry, let me take an example from friend to maybe line. Okay, if everybody, you know, is in not group line, yeah, but pairwise, you have all the friends in your line. Okay, if I give you information today, the class is canceled. In one step, you can send to everyone, right? Because she's connected to everyone. If I can do this with any of you, the class is completely connected. Now, I can still get message that the class is canceled from this person to that person, even though they may not have line connection to each other, right? So basically, it's not one step. You tell him, he tells him, he tells her, blah, 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 right? So there's a concept of connected and disconnected. In graph, as long as you can get to one person, okay, it's considered connected. So in this case, obviously, because in a play, you don't have one character that gets up on stage, acts his part, and leave and never talk to anybody else. Okay, that's kind of like a weird play. Okay, so you always appear with somebody because who you're gonna talk to, right? Except, you know, maybe soliloquy or something. But Hamlet speaks to himself, but he also speaks to other people. Fine. Okay, so there's really no play where somebody comes up and leave and you never see him again. Okay, so obviously this means they're all connected, but this person only appears directly, this person, on stage with this person. Okay, so maybe this is a private friend, but this person also appear with this person. So eventually, nobody's left out. Contrast this with the simulation that I came up with. Okay, this one again, same number. I basically use the same numbers just so that you can compare. So this is also 77 nodes or 77 vertices, right? A lot of people knows everybody. This is sparse. Okay, but still everybody's connected, right? Now let me try this. Now we start getting isolation. Isolation happens in two forms. First of all, you can consider this is a subnetwork. They connected to each other, but not connected with these. Right? Right? Connected, not connected with this. Connected with this. I don't know, maybe in Hamlet, you know, there's like the three witches that talk to each other on the wall. Maybe those are the three witches and they go away or something. Okay, the only audience see them, but nobody else does, maybe. I'm not quite sure. Okay, I think somebody saw the witches. Yeah. Okay, so in this example, if I have a message that the class is canceled, I can tell this person, but I cannot just tell this person, I have to tell this person and this person, and all these individuals have to be contacted separately, right? It's disconnected. So there's a whole bunch of graph analytics function like, I can't go to F1, can I? Something like is connected queue. You go to the help about graph function. It's okay. Okay. Menu. Okay. So let's say something like connected graph queue. In Mathematica, if the built-in function has a big Q at the end, it usually means a question like, is it connected? Connected in that sense, blah, blah, blah. Okay, anyway. Sparse array, blah, 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 blah. Now, so let's look at this again. Now, I mentioned that this number can be anything. Can be ordinal, nominal, interval, or ratio, right? What if it's the number of minutes that characters appear together on the stage. Then it's not 0, 1 anymore, right? It could be 15 minutes. It could be 17.2, okay? Or 2.5, 2.5 minutes or something like that, right? Because in graph data, they are so focused on relationship. When you talk about graph data, they usually mean 0 and 1. Okay. Now, in other contexts, when I talk about, numbers, if I'm talking about 0 and 1, I have to specifically specify, right? This is a Boolean number. This is a binary data. This is a binary problem. Otherwise, it could be anything. In graph, it's the opposite. Binary or 0 and 1 is assumed. So if you hear the word graph, you should think 0 and 1. If it's number other than 0 and 1, they would add the word weighted. Okay, it's just context, really, guys. Okay, right? So once again, if it's other context, you usually assume number is ratio scale. If it's binary, you would say it's a binary problem. But in graph, usually the binary is the case. So that if you're not dealing with binary, they would add the word weighted. Okay, weighted. Okay, and also there's, for big graph, you can't visualize, you can check, you can use Q, like is binary or that sort of thing. Okay, so I'm going to skip over that. Okay, anyway, so these fall under the properties: directed, undirected, symmetric. Oh, okay. Now, here's a funny thing. Nah, never mind. There's a subtlety. I don't know if you want to know, but you can actually have directed and symmetric. In other words, directed allows for asymmetry. Directed allows for asymmetry. So ij doesn't have to be the same as ji. But it just happens that in this particular case, it is symmetric. Okay? There's some situation where that happens. Okay. Again, I know you, you know me. Because I'm not a famous person. The only time you would know me is when I know you all as well. So it allows for this asymmetric. But because we're not famous, we meet each other at the same time. So it's symmetric, but, directed. Not that important. Okay. So all these things, right? Directed graph Q, symmetric matrix Q, and all that. Okay. Notice directed, undirected is a property of the graph. Symmetric or not symmetric is a property of the matrix. In Mathematica, even though I type the matrix, that data is matrix because it knows that this data is a graph example. It shows you as a graph, but technically it's just a matrix. Okay. So make sure you make the distinction between the adjacency graph, the adjacency matrix and the graph that's derived from it. Okay. So, but it's so ubiquitous, you convert graph to matrix, matrix to graph, and all kind of stuff. Anyway, so this is connected, unconnected. We talk about that. Acyclic, acyclic and cyclic. This is more property of more like engineering problem. Acyclic means you can't travel the graph in circle. Okay, so you can go to all other friends, but you can't come back. Think of graph as connection between highlights on a public forest reserve. Okay. Now you can imagine that this connection, right, between go from the waterfall to this thing to that thing to that thing. Now, if in artificial garden like in Disneyland, they probably make it so it is acyclic. So you can visit all the tourist attractions, but you don't come to the same place. Okay, but in nature park, in real nature park, usually it's cyclic. You can go to the fountain and go to the riverside and then come back to the to the parking lot and go back to the river, that sort of thing. So it's called cyclic. Okay, sparsity. Now, this is one of the most useful tools. So far, we've been showing you how to visualize the graph. right? And some basic property of a graph. But if you go back 2 lectures when we talk about cluster analysis, hey, some people are naturally clustered by location, right? What if instead of thinking distance, geographical distance, to say people clustered together, think of networking. This is a group, close, tightly knit group of friends, right? So instead of this one is random. This one I show you is random, right? Random. But you can imagine something like this. This is kind of obvious because it's separate. Now, think of situation where you are completely connected, but somehow there are 2 fractions. Okay, this group and that group is a lot more closely knitted. So think of these people. Okay, by location, they're close together. By location, you are close together. But in a way, this guy and this girl is not that far apart, right? But if I perform a cluster analysis, I can see 2 clusters, right? Now imagine that everybody reach a hand out so that this is a network, that is a network, and you 2 are also connected. Technically, everybody's connected. But behaviorally, they're kind of like 2 little cliques, right? Right? And that's called neighborhood. And that will be shown by, let's go down here. Where are we? Where are we? What did I say? Neighborhood, 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 neighborhood. Where are we? Where? Okay, so you just do enter, keep going enter. Now, this one, can you see this? My question is, what are you tempted to do? You're tempted to do cluster analysis, right? But technically, everybody's connected. So this is what I mean by this natural cluster. Now, if you use, excuse me, if you use the function, if you use the function neighborhood graph, where's that function? Where is that? Okay, let me ask this here. Might as well use some of the example. Neighborhood graph, I guess. Something like that. See what comes up with. Oops. NEIGSBORHOODGRAPH. Ah, there you go. Neighborhood graph. This is very clear. This is an analog, a graph. Graph plot. Graph plot. Okay, so this page, if you go to computation on graph, it has all kind of things. The one that I'm looking for is called neighborhood graph plot, I think. Let me. I have examples somewhere here. Wait a second. Neighborhood graph. Can you guys? Anybody found my use of? What did I do with it? Okay. Anyway, we'll come back to it. Let's just I'll go to test. Oh, this is vision. Okay. We'll find it somewhere in here. Anyway, so you can imagine that if you see something like this, right? If you see something like this, there's like a cluster here. Maybe you would add this guy and maybe this cluster, and certainly this is another cluster. Okay, so you can define maybe a number of closeness as if you have so many ways to get to each other in a short number of steps. Okay, so maybe this person to that person would take 1, 2, 3, 4, 5, 6, 7, 8. Okay, but among these people, if you don't get in one step, you can always get in 2 steps. Then it's very closely knit. So this is what this means. Okay, right. Now this is this is where we start to use machine learning. Okay, but in this case, sometimes it emerges from different tradition of analytics. Usually, it's not taught in machine learning class, but it's so useful. Okay, and this is called centrality analysis. Now, question is this: if you have something like this, like a feature like this, okay, is everybody equally important? Now, the word important here is very loaded. What does it mean, right? What does it mean, right? So let's say from a network or connectivity perspective, somebody is important, is someone who, if he's not there, the whole thing falls apart. Okay? It's not there. Now, in this case, if he's not there, what it means is that if he's not there, then the edges that connects to him is also not there. Okay? So let me show you this. Supposing, now imagine this is not the case right now. Supposing, okay, forget this node, forget this node, okay, forget this node and forget this line. What if there's a line from 1 to 3 to 12? Okay, 1 to 3. No, actually, we don't have to go far. There's an actual example. Let me ask you a question. This is a network of whatever, political alliance, right? You are only allowed to assassinate one person to take down the network. Who would you assassinate? Would you assassinate this guy? No, because it doesn't really matter, right? I mean, he dies, but so what? Okay. But what if you assassinate number 12? Okay. First of all, the team is divided in half. This guy can isolate, this guy can isolate, this guy can isolate. This thing and this thing never see each other again. Okay. He's even more important than 13 because without 13, you can still have this connection. Right? Now, I would not use the word important. I would use the word central. Who is central to the network? Okay. When you use the word central in a more general sense, okay, the definition of importance can be different. The number 12 is important in terms of if he's not there, the network falls apart, get disconnected. Okay. However, he may not be the most important in other aspects. For example, because so many people are over here, let's say this has got 1,000 people. Okay, it's got 1,000 people, and this has got like 5, 6, 7. Okay. In terms of efficient communication, if you were to spread gossip, would you spread to 12 or would you spread to 24? Right? Now, 24 is one of those where he gets bypassed. I think from 12, there's a connection from here to there. So if 24 is gone, the network doesn't fall apart. However, in terms of number of steps to pass message along this network, okay, average, okay, to get, if I put a gossip at number 12 and I say from 12 to 10, how many steps does it take? 1, 2. From 12 to 17, how many steps it take? 1, 2, 1, 2, right? Take this, all the number, add them up together, okay? On the other hand, I take same number for 24. The shortest number of steps to get to everybody, okay? Add them all up. Maybe it's more efficient to spread my Roomba in 24, right? Right? So these are the centrality, okay? Now, let's be a little bit more casual. When you ask about somebody who's popular, okay, think of centrality as popular. You say, who's popular? You usually think of somebody who knows more people, right? Now, imagine that there's a guy in here who knows all these people, right? But indirectly, everybody knows everybody anyway. So without him, the network is still okay. You have those kind of friends, right? He sort of like knows everybody, but actually the friends that he knows eventually know each other anyway, maybe not directly, right? Without that person, the network doesn't fall apart. But if you count just the number of line that emanates from or to him, he's got the biggest number. Okay. So here's an example. Okay, I want you to do a little mental gymnastic. You guys remember last time we talked about cluster, right? I can form cluster in terms of closeness, but there's an example of the two communities across the winding river, right? Where even though you are close, you can't get to each other. So it's contiguous closeness. So it depends on the definition. Okay, philosophically, it's called organizing schema. Okay, how you define closeness. That determines unsupervised learning algorithm. Same here. If my unsupervised learning algorithm say, tell me who is important. In terms of, if he's not there, the network falls apart. In this case, it happens to be obvious. I think maybe 12 or maybe 24, actually. I don't know. They're probably 12. Okay. But if I measure in terms of minimum distance, in terms of minimum number of steps to pass gossip, okay. By the way, technical word for gossiping in mathematics is called message passing. In computer, it's called message passing. Okay, so from one computer to one computer, that's one traverse. When you take from this computer to that computer, it's another traverse. So in the internet, you can count the number of nodes to get to. So vertex, the same thing. Okay. So passing gossip among friends, same thing as passing internet HTML, internet protocol query. Okay. Right. So now, this different algorithm, there's no one that's better than the other. It's not like regression where you want to get accuracy. Now, what's good depends on what your organizing schema is. Okay. Okay. So I can ask, in this group of friends, in terms of importance, in terms of centrality, I can ask in different terms. Okay, I can ask different terms. Let me let's take a 5 or 10 minute break. Then when we come back, we'll start to do the algorithm. I'll show you that in mathematics, it's dead easy. It's, but you just use different name and then it'll come up with the result. Okay.